Here we go. All right, so homework from chapter 12. We're going to finish up chapter 12 today. So homework from chapter 12 is due on Wednesday. That sounds right. Yes, I'm losing track of my days. People are nodding at me. Good. All right. And then today, the second half of 12.4 and 12.5. Monday, 13.1. Wednesday, 13.2. I don't think we're skipping around. Next week, Friday, whirlwind tour through everything. Not true, false, because the final exam is not cumulative. Whirlwind tour starting with chapter 8. Whirlwind tour starting with chapter 8. And then Monday's the exam. Questions about anything? Proof notebook, homework, exam, anybody, anything? No? Good? Happy? Okay. All right then. So we are... There we go. Talking about injective and surjective functions, right? And we did some examples last time. So I am going to get the definitions up on the board. We're talking about function composition in conjunction with injective and surjective. So that's kind of what we're doing today, merging these two concepts that we've had before. We had injective and surjective functions. So those are the definitions I'm going to put up. And then we did function composition. And today we want to talk about how those kind of intersect. And then we'll get into inverse functions, which based on the reading assignment, I don't think people had tons of problems with. So remember the definitions. Injective, two ways of doing this. If x is not equal to y, then f of x is not equal to f of y. Or if f of x equals f of y, then x equals y. So that was your definition for injective, right? One-to-one. And surjective, we got to get the for all and there exists in the right spot. So for all y, we'll go with little b instead. For all little b living in capital B, there exists some a living in capital A, so that f of little a equals little b. The domain and, the codomain and the range are the same for surjective. Codomain and the range are the same for surjective. That's your definition there. All right, and then remember we also talked about function composition, right? G circle f of x was g of f of x, and you can do it the other way around. F circle g of x is f of g of x. So function composition. Okay, good for review. Ready for a theorem? We're going to prove a theorem today. It actually comes in two parts. So we're going to prove two parts of a theorem. And we'll put it on here. I don't think I have enough space to do the whole thing, but two parts of a theorem. So theorem 12.2, I'm going to call it part A because I'm breaking this theorem into two parts. Theorem 12.2a. Here's my hypotheses. First of all, f going from A to B is injective. And secondly, G going from B to C is injective. So I've got two injective functions that I'm starting with. F is going from A to B. That one's going to be injective. And G is going from B to C. That one's going to be injective. So two injective functions that I'm starting with. And my conclusion, remember we are merging injective, surjective, and function composition today. My conclusion, G circle F going from A to C is injective. So if I have two injective functions and I compose them, I get another injective function. Two injective functions composed give me another injective function. Basic idea of the theorem makes sense? Give me a thumbs up there. Basic idea, okay? All right, we're gonna prove this because it is a good example of how a proof with injective functions works. So here's my proof. We'll do what we know and what we need to show. So let's go with x and y live in capital A, and I need to show that G circle F is injective, right? That's the function that I'm trying to show is injective. I could use either the first definition for injective or the second one. Remember, the first one works a little bit better if you're trying to provide a counterexample showing not injective, and the second one works a little bit better for a proof because equals are a little bit easier to deal with in a proof as opposed to not equals. So we are going to assume this right here, G circle F, is the function that I'm trying to show that is injective, right? So I need to assume that G circle F of X equals G circle F of Y. And then my need to show is that X equals Y. The function that I'm trying to show is injective is the composition, G circle F. Do we see where that's coming from? That's the function that I'm trying to show is injective. So that's the function that I'm working with in the definition. Everybody see why I have a G circle F there? Nod at me, give me a thumbs up, something why I have a G circle F there. Yes, okay. All right, so we know that G of F of X equals G of F of Y, right? I'm just rewriting composition in terms of the ofs instead of circles. So G of F of X equals G of F of Y. All right, here's a jump. Because G is injective, this implies something. Because G is injective, this equation is going to imply something for me. So here's what I want you to see. G of something is equal to G of something else. Yes, my squiggly underlines are the something. G of something is equal to G of something else. And therefore, because G is injective, those two somethings have to equal each other. Kind of think about this as sailboats, right? G of sailboat is equal to G of flower, so therefore sailboat and flower have to equal each other. Do we see that? If G of sailboat equals G of flower, then sailboat and flower have to equal each other, okay? So sailboat is F of X and flower is F of Y. So because G is injective, this implies that F of X equals F of Y. Because G is injective, I know that F of X equals F of Y. Sailboat and flower, seeing it in terms of sailboat and flower? Yes, good, okay. Now we're basically done. So because F is injective, and this one's the easy part. We've got F of something equals F of something else, two somethings here. So because F is injective, this also implies that X equals Y as desired. That's what we wanted to prove. So this is one of those unusual proofs where we don't start on one side of the equation and work our way to the other side of the equation. I've been hitting those really, really, really hard over the course of this semester, justifiably so, because we usually prove an equation is true by starting on one side and working our way to the other side. But sometimes you can start with an equation that you know, tweak it, mess with it, etc., and get to an equation that you are trying to show without starting on one side and working your way to the other side. All right, we've got an as desired, we've got a smiley face. That means we are done with our proof. Are we good with our proof? Give me a thumbs up, show me yes, we're good with our proof. Yes, nodding, thumbs up, everybody's happy. Excellent, okay. That was theorem 12.2a. So theorem 12.2b is the same idea except with surjective. So theorem 12.2 part B, here's my hypotheses. Same thing, but with surjective. So F going from A to B is surjective. And G going from B to C is surjective. Sorry, that's terrible handwriting. Conclusion is that F circle G going from A to C is surjective. So again, if you compose two surjective functions, you get a surjective function. If you compose two surjective functions, then you get another surjective function. That's what this is saying. We want to prove this because we want to play with properties of surjective as well. So here's my proof. We want to be a little bit careful because, oh, that's backwards. I have F circle G. That should be G circle F. That is backwards. Let's get this as G circle F instead of F circle G. Sorry about that. G circle F going from A to C. My bad. Sorry. All right, we want to be a little bit careful in this case because our domain is what we're used to, that's A, but our range is not what we're used to, that's C. So we need to let little c live in capital C. This is my for all, right? So I can't pick anything about little c. I'm just picking some generic element in there. And I need to show there exists some little a living in capital A so that G circle F of A is equal to little c. That's my need to show. So if I start with something in the codomain, I have to show that it has a preimage in the domain, and preimage in this one is going to be preimage of G circle F. That's the function that I'm trying to show is surjective, so preimage of G circle F. Okay, let's write down what we know. So because G is surjective, we know there exists some little b living in capital B so that G of B is equal to C, right? Because G is surjective, and I should say also, and little c lives in capital C. So because G is surjective and little c lives in capital C, we know there exists some B living in capital B so that G of B is equal to C. G, looking up here, I wish I could point at the board, but I can't, so we're doing it this way. G goes from B to C, right? So if I've got something in the codomain of G, it has to have an image. Same idea with F. So because F is surjective and little b lives in capital B, we know there exists some little a living in capital A so that F of little a equals little b. So I've got something in the codomain of F, and therefore it has to have a preimage in the domain of F. Seeing that? If I've got something in the codomain of F, it has to have a preimage in the domain of F. Are we good? Do we see where that's coming from? Something in the codomain has to have something in the domain. All right, so now here's my need to show. I am trying to show that G circle F of A equals C. So we're going to start on one side of this equation and work our way to the other side of this equation. Here we go. We know that. We know that. G circle F of A is equal to G of F of A. Do I know anything that I can plug into that equation? Either unmute yourself or give me a comment. Alyssa, yes, you're nodding. You nodded at me. That was brave of you. What can I plug into that equation?
For F of A, you can plug in B.
Absolutely. I can plug in B for F of A. So this is G of B. Cool. Somebody else besides Alyssa, anything I can do with that equation to hopefully get where I want to? Grant.
E of B equals C.
That is equal to C. Yes, that's equal to C. That's what I want. That's my right-hand side. And so we can say, therefore, G circle F is surjective as desired. Yay. Okay, so function composition preserves injective and surjective. That's the way that we would technically say this. Function composition preserves injective and surjective. When I say it that way, does that make sense? When we compose two functions, right, if they both have an injective property, the function composition is still going to be injective. If they both have a surjective property, then the composition is still going to be surjective. So function composition preserves injectiveness and surjectiveness. Any questions on this before we jump into 12.5 and inverse functions? Anybody, anything? Okay, let's then